again. Okay, so that was the part where you do the inferencing, right? Inferencing, you have a sample data, you do calculation, and then you inference about the population. Now the important part of the session is that you have a two group of data, and then you want to discuss, you want to find out whether they are different or not, right? The most of the statistics is around t-test, p-value, and you might have read some in the papers that they talk about a lot of tests, right? The chi-square test, the p-value is lower. What are all these things? We are going to talk about this, right? So in this session we will talk about only two groups. That let's say that you have two groups, you want to find out whether they are different or not, and if they have any relationship, right? And you will be doing a lot of experiment like that. If I remember correctly, Rashida was telling me that you will be doing experiment like collect some EEG or calculate the heart rate or blood pressure, or do some experiment with that, right? And try to find the two groups differently or not, right? So this is all you will need for that. So in this we will talk about hypothesis testing. What is hypothesis, what is testing, what is p-value, what are the type of errors we have, and what happens with the multiple testing and statistical power, which again in a little more detail, which we will cover in the lab session. So this is the proper flow for the any experiment, right? We first define the hypothesis. That's the most important thing. In other in my previous course also, this part was not there. I intentionally put it there, that first you define the hypothesis, then you collect the data or acquire the data. You can collect it from other sources, or you conduct your own experiment. Then you perform the test, estimate the p-value, and interpret your p-value. That's it. Very simple, right? Now let's see how do you define the hypothesis. So hypothesis is a statement which you say, like you kind of claim something. That's your hypothesis, right? So it's in science, every time you have a hypothesis, you have to prove that that hypothesis is reasonable statement or not. And to prove it, you have to perform a test against its contrary, right? Let's say if I make a hypothesis that okay, this cup of coffee or this style of coffee is best for the health. That's a statement, and I can't just say it, I have to prove it, right? And I have to prove it against the contrary, that this is not the best, right? So in science, every statement has to be proven, right? And we have to prove it by some data and by some experiment. When you have a statement, you have always two kinds of a statement: null hypothesis and alternative hypothesis. Null hypothesis is assumed to be true, which is the contrary one. That's your enemy. This is always enemy, because this is always true, always. So you don't actually have to do anything for proving it. It is considered to be true always. Alternative hypothesis is actually your hypothesis, your claim, that you are making a claim against anything. And that's why burden of proof is on you. You have to prove your statement, right? So burden of proof is a very common statement, that if I say it's burden of proof is on you, that's mean I don't have to prove myself, you have to prove yourself. You have to prove you are right, I don't have to prove that I am wrong, right? Like this. It is the same thing as in the judicial system that we have. Anybody who is in the criminal case, it is innocent unless proven guilty, right? So when they fight in a court, its burden of proof is on the prosecution. They have to prove that he is a criminal or he committed a crime, and then other party only have to just protect that he is not. But he doesn't have to prove that I am innocent. You have to prove that I committed a crime, right? It's a burden of proof is on you, not on me, right? So same thing. When you make a statement, you have to prove that it is true against the normal known thing or the assumed to be true thing, right? So before we come to this one, which is very interesting, let's see one of the very simple example, that we want to find that is there a lung function different between genders. That's a statement, right? That's the kind of experiment we want to design. What would be my null hypothesis? Actually, it should be already, it's written. Yeah. So my null hypothesis is that the lung function in man is equal to lung function in woman, which is assumed to be true. Alternative hypothesis is lung function in man is not equal to lung function in woman. That's what I have to prove, right, for any experiment and data. If I don't prove it, so burden of proof is on the alternative hypothesis. My whole experiment is to reject the null hypothesis. Okay, and alternative hypothesis can be also with the side. You can say it's not equal to, and you can say, okay, the lung function in the man is greater than lung function in the woman, or it is less than woman, right? That's another kind of a hypothesis you can make, but you can just say that it's not equal. For example, if I say teaching method A is better than teaching method B, that's again a statement, but I'm saying it's better. I'm not saying it's worst. I can say it's not equal, that's one statement. I can say it's better, then it's another statement, right? So one of the interesting question that I remember asking is this. So let's say that you say that your friend is always late, or your friend is saying that you are always late, right? How would you make a statement out of it? Proper hypothesis around it. Tell me, what would be the null hypothesis? Your friend says you are always late. So what's the null hypothesis? What? You are not late. You are not always late. Again, use the qualifiers, right? And what would be the alternative hypothesis? You are always late. How would you prove it? What? No, you will collect the data, perform the test, calculate the p-value, and show it that, see, my p-value shows that you are always late. That's exactly what we are going to do. Yes?
Why is the p-value so important?
Okay, so p-value tells you that probability, that how bad, like, I'm just very quickly telling you, but we'll come back to that. P-value tells you that your possibility of being wrong, and we want it to be less and less, and we have a cutoff. If I'm less than, if my possibility of being wrong is less than 5%, I'm good enough to go.
Okay, so your value, say there was 0.5 for p, it means you're right 99.5%?
Yes.
Okay.
So you're 95% confident that you are right. Again, that 95 keep coming back again, right? So that's the p-value tells you again, right? We'll see that, how to calculate and how it makes sense, right? So you got the idea, right, that your friend is determined to prove that you are late. So what he will do, he is going to collect the data. Every time you come in, he put the data, put into the two tables, and perform a t-test and calculate the p-value and show it to you. See, you are always late, right? And if you want to prove it that you are not always late, you have to do the contrary, right? Another example, let's say that height in a class A and B different. What would be null hypothesis and what would be alternative? Height in class A and height in class B is same. That's a null or alternative? Null. And different is the alternative, right? So that's designing the hypothesis, right? We will come back to that again, but how to actually properly write it. But once you write it, you are almost done. Like you are halfway through, because now you know exactly what to do, right? And then second is acquiring the data. Acquiring data requires conducting lab experiment, collecting data from the other sources, right? Again, when you collect the data or acquire the samples, you have to make sure it's representative and it's large enough. If it is not, then you can't claim about the entire population. You might have a different claim, but you don't have the entire population claim. Performing tests is very simple. You have a data from two groups, you give it to software, and it will spit out two things: test statistics and the p-value, and you have to infer. There's a good calculation around it, but good news is that you don't have to remember the formulas, you don't have to remember what they do, only you have to interpret it. For that, we have softwares that will do, and for this we will have SPSS. We'll be using it, right? And the question is which test to perform, which is little complicated, but we'll make it very simple. So where you have a software, it can perform all the tests that you want, but you have to choose the right test, right? So these are the four kind of main tests that we'll be looking into. What test you want to perform depends on what kind of data you have. Is it a paired or unpaired experiment? Do you want to perform parametric tests or non-parametric tests? And then you choose the test accordingly, right? We'll come to that, right? So don't worry about it much. After performing a test, so you have a hypothesis, you collected the data, you chose the correct test, and you performed the test using software, and you got the p-value, right? Now p-value is with the right test, actually p-value will tell you a lot about your test, right? P-value is the probability of obtaining a difference or the effect by chance. So for example, if I have two data sets and I want to make sure that the height of a class A is different than class B, I collected the height of everybody in the class A and everybody class B, right? I checked with the p-value will tell me with the test, and p-value comes out to be, let's say, 0.01. So it is telling me it is different, and the possibility you might have got this by chance is 1%. That means there is a 99% chances that your difference is a true difference. It's not random, because this is a possibility you might just get it for random, right? So let's go back to the animation, and we'll So let's go to the two groups thing, right? And so let's say that this is the two different groups, right? Class A and class B, and x-axis is the height, right? I take the 5 sample from class A and 5 sample from class B, right? Their height is on this axis. The x-axis is the height, right? The blue 5 sample height is this, and that's mean. Green 5 sample is this, and height is this. My question is, are they different groups, right? Right now they look very different because we know the true distribution already, right? We plot it like this, and this is the difference between the means, and we will perform a t-test to prove it that they are different. In this case, p-value might come up to like less than 0.05. So there is a good chances that this is right? But let's say that if I keep doing it many times, let's clear it to it again. There is a chance, and very less chance, that I will get something very weird, which is, okay, let me just do it. I think the variation is good. So look at this, this and this p-value, right? So there's a good chance that not very good chance, but there's a chance that I will get the samples which are actually randomly come together, right? And my means are very close together. What are the chances? In this case, very less than 5%. It all depends how far they are the actual distribution. So that's your p-value. That's the alpha cutoff that we put. Alpha cutoff value is the 0.05. If p-value is less than 0.05, we consider that to be alternative. We accept the alternative hypothesis, right? And there is another possibility that they are actually same. They are all together, right? And I took the sample from the two same distribution, and the mean is still far away, right? And I might conclude, because p-value comes out to be very low, and I might conclude that they are different whereas they were same, right? How many times it can happen? It can happen very less number of times. Look at them. They are almost overlapping to each other, right? If I take any time sample, they are going to come close together. But there is a chance which we are saying by random, 5% chances that they might come far away. And then you might conclude that they are actually different group, but they were actually same. You got the point? I think that you are confused, right?
So the bigger the sample size, the more accurate the p-values will tell us?
No, the more bigger sample size has an impact, but the distribution, if they are true, like so right now our question is, if they are actually two different distribution, and your p-value suggests that they are different, good. But they are not two different distribution, and your p-value suggests that they are different. That's the problem, right?
How do we know that?
You never know. But there is a chance. That's why we are talking about that there is a possibility, and that possibility is very low. In this case, they are the same, but you saw the first example, they were very different, mean was different. But if I take it again, it might not. If I do it one more time, it might not. If I do 100 times, 5 times, I will still get them same. So that's the randomness, right? That's the possibility. You can never be completely sure about anything. You can be sure about some extent, and that's the p-value is for, right? P-value is a possibility. Even if your test is saying that two people are different, two groups are completely different, there is a possibility you are wrong, and that possibility is very low. That's the p-value for, right? And some people actually show the complete p-value, that my p-value is 0.00001.12345, to show it that, see, I am very, very sure that I am not wrong, but still there is a possibility that you are wrong, right? Okay, so p-value tells you that p-value range from 0 to 1, and you interpret that p-value accordingly, right? Again, it's not possibility of making an error, it's a possibility that what are the chances that your conclusion is wrong. Okay, let's see now. So whenever you do any kind of scientific study, you have one statement, hypothesis, you always go this kind of a table, right? What is your true thing and what is your false thing? Like, so this is saying that your null hypothesis is true, and you accept the null hypothesis. So okay, so when p-value is less than 0.05, you reject the null hypothesis. Okay, so that means possibility of these two things becoming same is very less, and then you reject the null hypothesis. You accept the alternative hypothesis, right? So the true condition is that your null hypothesis is true. Your experiment says that you accept the null hypothesis. Your HP value is greater than alpha, and then you fail to reject the null hypothesis, or you accept the null hypothesis. That's fine. That's good enough, right? Another thing, that null hypothesis is not true, and you reject it. Your p-value is less than alpha, and you reject it. You are good to go, right? We are still not making any error. But when your null hypothesis is not true, and because of some test or randomness, you actually reject the null, alternative hypothesis, or you accept the null hypothesis, you are making one kind of error. That's called the type 2 error. And if your null hypothesis was true, but according to your test you reject it, you are making another kind of error. Let's make it simple. Let's say that there is a criminal, and the null hypothesis is that he is not criminal. Alternative is he is criminal. The court decided that let's to punish him. That's mean decide that he is a criminal, but actually he was actually criminal. So court is not making any mistake. He was not a criminal, and court decided he was innocent. That's fine. That's also good, right? Now let's go to the error part. He was innocent, and court decided to punish him. That's one kind of error. Another kind of error, he was not innocent, and court actually concluded that he was innocent. That's another kind of error, right? So one of them is a type 2, one of them is a type 1, right? The judicial system is that it's okay to leave a criminal as an innocent, but not to punish an innocent as a criminal. That's their philosophy. So they kind of put little bit weight on that system, right? So some system try to minimize this, another system try to minimize this, most of the system try to minimize this, right? It's all about do not fool yourself. You are getting a data, you are getting a test, just make sure that your data and test is correct, you are getting a p-value, but is your p-value correctly doing what you are actually expecting itself or not, right? So there are the possibility you might be wrong, right? So just to make sure that. So there are two different kind of errors. Let's understand the error again with the one example. So let's say that I think that there is a tiger over there in this, but null hypothesis is not tiger, it's zebra, and alternative hypothesis it's tiger, right? Now what's the condition here? Null hypothesis is it's a zebra, alternative is it's a tiger. What will come here? So if it was zebra and my test, I conducted test to find out, and I concluded yes, it is actually zebra. I'm right, no mistake done, I'm good to go, right? So null hypothesis, I accepted the null hypothesis in this case, right? What's this? I rejected the null hypothesis, right? So no, sorry, it was H2 is false. So null hypothesis is not true, which is alternative is true, and I actually accept the null hypothesis. So it's a type 2 error. Think it's, am I confusing the terms here now already? Is it making sense? Okay. Again, we come to this thing. If there was no tiger, I said there was a tiger, I said the tiger, good to go. There was no tiger, I concluded there is no tiger, good to go. There was a tiger and I said it was zebra, that's one of the problem. There was a zebra and I concluded that was a tiger, that's another kind of problem. Which is a fatal, that's up to your problem, and one of them is type 2, one of them is type 1. Okay. Yeah, so type 1 is the alpha of rejecting the true null hypothesis. It's again a false positive, but positive and negative is just a semantic, depending on the detection problem, but it's fine. So for rejecting the null type 1 error, we have alpha value which is 0.05. That means there's a 5% probability that you might be wrong. Type 2 error is failing to reject the false null hypothesis. That's mean alternative hypothesis is true, and this is the power of the statistic. So there is another term which comes beta, which is what is the possibility that you are actually rejecting the alternative hypothesis which was true, right? So that's the power of the statistics. It is calculated with some numbers, and that tells you that how many samples you need for the study to prove it properly, right? Okay, p-value in summary, we just go as a one cutoff 0.05, some go with the 0.001 for 99% confidence, and there when we have this, we actually use the word significant or the statistical significant. So we do not use the word significant until we actually find the statistically significant evidence that two things are different, right? So in a normal sense, significant means anything important, but in statistics, significant has a good meaning about it, right? So we say p-value is less than 0.05. We say, oh, our study suggests that there is a significant evidence that these two groups are different. That's how we write it, right? P-value less than 0.001 is a strong evidence, like that. Multiple testing, we are not going to come that. Yeah. So significance and meaningful. So we still have time, right? Yeah. So there might be significantly, like there might be two groups which have significantly different from each other as a height or a weight in a class, but that doesn't mean that there is anything meaningful out of it. We have to also check how much difference we are talking about, right? So not every time you get a p-value less than this going to make any difference, because you have to check that what's the difference actually we are talking about, right? So there is example here. So example is that we have a group of male and female, mean value is this, it's about, let me see, what is this about? Yeah, it is some study. We have mean, we have standard deviation, this, right? We got the difference of the mean is this, p-value is this, right? This is a lung function, I think so. Yeah. P-value is this. So we concluded that yes, man and woman are different in a lung function because p-values suggest that, right? How much different they are? This much different. And this study, difference is only this. The number of samples are less, but difference is this. P-value is this, right? So that's one of the things. So p-value already is saying to reject it. It's saying just reject it. There is no possibility that they are different, right? The point was that whenever you actually see there's a significant difference, if the difference actually is meaningful or not, that's another question, right? You can't just say that, okay, there's a significant difference between the height of two classes and the difference is 1 millimeter. It doesn't make any sense, right? It's not meaningful, right? So you have to talk about the differences of mean also, which we will see in example. Again, this is a dots for this lab session. And to choose the correct, I think we have time. Yeah. So now how to choose the test. Whatever we are left out, we will continue in the lab session with the starting, and then we will actually do some experiment with some data and perform some test. So how to choose the correct test. So we have seen a big tree, right? So first thing is the numerical and categorical. If it is a categorical kind of a data that you have, right, you go for this. If it is ordinal, in categorical you have ordinal or qualitative, right? If it is ordinal and if it is a paired test, you go for paired t-test, and if it is unpaired, you go for Mann-Whitley test. If it is qualitative, for paired you go for McNamara, and for qualitative you go for the unpaired you go for Pearson. Still there is a question of pairing and unpairing thing. We will see what is a paired and unpaired thing. So whenever you have data, in the experiment you check if it is a paired experiment or unpaired experiment. Unpaired means also independent and paired means dependent, right? So the simple example for that is like this. In unpaired, we have a two different group of points, right? They don't have one-to-one connections there, right? And they can be same, but they can be same different number of the samples also. Here you can have 100, here you can have 5 or 50, something like that. Ideally we want them to be in the same order, they can be a little bit different. Paired, you have the same patient or same person at least, right? So same, like ideally that you want to test that whether ECG of a patient's before and after exercise. So that's the same one. So you have same people, you are checking the difference of a same person before and after treatment. So it's a paired one. When you have one-to-one connection between the data points, it's paired. Here you will have same number of people as in the group A and group B, right? So that's how you decide whether it is paired or unpaired. Fine. I think I should have put it there. When you have data, you decide which is your paired study or unpaired study. That's the first thing. Second thing, you want to choose, do you want to perform parametric test or non-parametric test, right? So parametric and non-parametric comes with little bit of assumptions. So parametric tests are tests which relies on some underlying distributions, right? So if the data should be normally distributed, and there are even tests for that, right? The first assumption is that data should be normally distributed. It should have nice bell curve. If it is not, then we go for the non-parametric test, because parametric tests everything assume that your data which you are giving them is nicely distributed. So let's see a few examples and then we can actually stop after that. Yeah, so that's the whole thing. You have data, choose it's paired or unpaired, go for parametric or non-parametric depending on the assumptions, and accordingly perform the test. Okay, there is one example. Question is average age of a man and woman different in a given data set? Tell me, is it a paired or unpaired? So you have to check always three things: paired or unpaired, normality for the parametric and non-parametric, and equivalence of variance. We will see that these two things again. It will come to that. So is age of a man and woman different in a given data set? Is it paired or unpaired? Because they are totally two different groups, right? What's the null hypothesis? It's the same. Alternative is not the same, right? That's in the short we can write it. Paired, it's unpaired, right? So from this category we go to unpaired. Now we have to decide whether to parametric or non-parametric, right? So for testing whether you should perform parametric test for two groups, you have to check whether they are normally distributed and they have equal variance or not. Normally distributed, this is a distribution of age of I think men and women. Do they look normal? Roughly they look like normal, right? So the question is that, yeah, it's right now in my eye it look like a normal, maybe not to you, so but you don't have to worry about it. There is another test which can tell you whether it is normally distributed or not. It's called test of normality, which we'll see. And there is another test if it is normally distributed, we go for dependent test, or not dependent. No, if it is normally distributed, we go for parametric test. We already are here, right? It's independent. This is dependent. Parametric. If it is normally distributed, we go for parametric test. Parametric test is student t-test independent, right? So in this case, we will perform a student t-test. And then when you perform a t-test, it gives you test statistics and p-value. What do you conclude? This is exactly what you are going to get from the test. You have the data, you form the hypothesis, you wrote the alternative hypothesis and null hypothesis. You test whether it is paired or not. To choose a test, you have to check paired or not, normality and variance. Variance, we will come back to that how it make a difference, but let's leave it right now. So we checked it's unpaired, we checked it is normally distributed, we perform a t-test, we got the t statistics and the p-value. What do you do now? Do you accept or reject the null hypothesis? Reject the null hypothesis. Reject the null hypothesis means, what is the p-value? 0. Yeah, so what is the cutoff, normal cutoff for the p-value to be accepted? Is it? It is greater, right? So statistically you have to reject it. You can accept it with the 90% confidence, but from 95% confidence you have to reject it, right? We go for 95 most of the time. So p-value is not low enough to reject the null hypothesis. It should be less than 0.05. It's not. So you accept the null hypothesis. In case even if you reject it, let's say that you're rejecting it with a 90% confidence. You say, statistically it is significant that age of a man and woman in this data set is significantly different. How much different they are? That's another question that you always have to ask. It's not all about p-value, which is going to tell you that whether test is significantly different or not, but you have to say how much different we are talking about. So what's the difference between the age in the man and woman? Just check the mean. Mean of man is 45, mean of woman is 46.83. Even if you accept it with 90% confidence, you will say, 90% confident, I am sure that the age of a man is different than woman in this data set, and the difference is 1.6 years. Is it big enough? It's not that, right? But it might be in your case, in a study, it might be. So the point is, even if this was very low, your difference is not that low. So always a significant doesn't mean meaningful. A test comes out to be significantly different, doesn't mean it has any meaning until you show it there is a meaning, right? That's another example. Is the average lung function in a man different to one in women in general population? So what's the null hypothesis? Same lung function. And alternative is? Different. That's what the shortcut to write it. Is it paired? Is it paired? Unpaired, right? So we go in that tree, unpaired side. Is it normally distributed? Look at the distribution. Yes. If you're not sure, always perform a test to do that. SPSS does it for you. Don't worry about it. Equal variance, another thing that SPSS does it for you, so don't worry about it. So we perform a t-test, independent t-test, okay? And that's a test is giving you. What do you conclude? You reject the null hypothesis and say that my test says that there is a 99.9% possibility, or with the 99.9% confidence I can say that the lung function of a man is different than woman. How much different they are? You subtract the mean. Almost 1,000, right? Yeah. So the difference between the mean. That's it. Another example. Has the lung function changed after intense exercise in the study? What's the null hypothesis? No change. So how do you write it? Mu before exercise is equals to mu before after exercise, right? And we can actually write it also like the difference between the before and after is 0. An alternative is it's not 0, right? Is it paired or non-paired, unpaired? It's paired, right? We're talking about the same individuals, right? The data, we don't look at, when it is a pair test, we don't look at the individual distribution. We look at the distribution of the difference. So there is no variance check. And the variance check, when we see the variance check here, equal variance, before performing a test we have to check whether the variance of this group is same as this or not. And if it is not, then we have a little bit different formula to do it. But again, SPSS is going to do it for you. For same t-test, the formula just become different. But otherwise, if it is same, then you have a different formula. That's it. But it's still same test. Now, when we go for the pair test, we don't look for the equal variance. Why? Because we don't have the two groups anymore. We have the difference. And the distribution of difference should be normally distributed. Is it normally distributed? Yes. Which test you will run? So you run a test according to the tree, right? And then you find the t statistics is 38, p-value is less than 0.01. What do you conclude? Reject the null hypothesis, and you say that yes, there is a difference. How much difference is there? What's the difference between the lung function before and after? I don't have to give you everything, right? Do I? This is actually the difference, right? This distribution is the difference for every man or woman before exercise, their lung function, or after, right? So that's the difference, and the mean of the difference is this, which is exactly that you want, right? So that's the difference. Fourth example, I think we are almost done. Has the total I don't know what is that, changed over the time in 10 years? Is it paired or unpaired? Paired. Null hypothesis, not changed. Alternative, change. Paired, you got the t-test. Is it normally distributed? Look like. You perform a test, you got the t statistics, p-value is greater than this, what do you do? Exactly. And the difference, again, I think the calculation is not here, but yeah. So that's what we will do in the lab session next. Yeah. Any questions so far? Yes.
I just wonder about the false positive, with the false positive, the beta. What is the power representing to? The confidence interval, you mentioned that sure we are in the population that 95% we are sure, but what's the power represent to?
So power represent like, okay. So in this group, let's say that there are two groups which are actually different, right? And with the one test, let me just clear it. With the one test, you actually concluded that they are same, right? So you accepted the null hypothesis wrongly. Null hypothesis was that they are same, but actually they are different. And you accepted the null hypothesis because your sample says that mean is very close or something, right? So for this happens only when two groups are actually different, and you want to actually make sure that they comes out to be different. So there is a different statistics that the power statistics tells you that how much of the difference. So that tells you that the sample size comes to that. So if they are, let's say that right now they are still looking very different, let's say that they are this much different, very small difference, right? And we check, we might just accept the null hypothesis that they are same, but there is a small difference, right? So question is that how much difference that you want to find out will calculate that how many samples you need in order to avoid this. So even in this case, right now it looks fine, but if I go for, let's say, 5,000. Oh, wait, this is, oh shit. It's gonna, okay, let me. So if I do a very high number of sample, you might, even if they are same, you might find a small difference. P-value might come out to the very less, right? But the difference might not. The question is, the smaller the difference between two groups is, higher the number of samples you need to in order to find them different from the test, right? So if the difference that between the man and woman height, if you want to find, and you say that at the minimum difference that I want to find is 1 feet, then you need a different data set, different number of sample set. And if you need, let's say that 1 millimeter, then yes, even checking the smaller one, you want to detect that, then you need even the larger number of data point.
One more question. Why do we put the cutoff value at 80%? Because the formula is 1 minus 0.8. So isn't if the power higher, maybe 0.95, isn't it not utilized?
Let me go to, I think, I don't know where was that. Yeah, here, right? So normally it is considered that at least you need to have the 80% of the power, right? Which means the beta should be 20%. That means there should be a 20% chances that even if that you might accept null hypothesis even if it is wrong. So that's the power. Higher the power is, lower the possibility of accepting the null hypothesis even if it is wrong. You might conclude in a test, and many times you will, that no, these two groups do not have a differences, right? That is either actually they are not different, or you don't have enough sample to prove it. So you don't have a good power. So what's the chances that you might be wrong? 20%. You want to make it less chances, improve the power. How do you include the power? There's a calculation behind the calculation of the number of samples. More samples, how much difference you want to find out, include more samples, you will have higher power, and then you will have lower chances of accepting the null hypothesis when it is wrong.
So the consensus is like at least we must have power of 80% for conducting study.
Yeah. For like that's a normal condition, but you don't have to have. Like just for the 5% thing, you can have the 99% of that, or like 90%, or the 1%, something like that. So it's a normal, like how normally people do that, but it doesn't have to be exactly the same, right? But in the papers you will find something like that. Any other question? You had some question?
Maybe just in the example that you showed, there are p-values and statistic. What's that?
Yeah, T statistics. Yeah.
What is that?
So when you you calculate a p-value. Before p-value, you always have some number, which is, yeah. So every time you perform a test, you have one test statistics. Sometimes it is F statistics or T statistics. It depends on some distribution. It's some crazy number which we use to calculate the p-value, right? But this number also tells you a lot of things. So in this case, it is a positive. It is 20. Higher than some value, it is going to be something. In some tests, you will find it positive or negative. So it might tell you that if it is, let's say that you want to say it's not equal, right? So the positive value say that it is greater, and negative will say it's less, right? So this T statistics for every test, it is different. It's differently formulated, but there is extra number that you always get when you perform a test, other than p-value. But p-value completely depends on that. So ideally, you take care of the p-value more, but T statistics also tells you a lot of things.
It's like comparing between the men and women.
Yeah.
If it is positive, so men on more than women.
Yeah, I had to check which exactly test was performed. But if it is positive, yes, it is a greater, and if it is negative, it is less. Yeah.
In two groups.
Yeah, yeah. So sometimes it is always only positive, but that's what I have to check, that which test is performed. It's not always the sign, it's the intensity. Like the test statistic is 3 or less, that means you will almost be 90% sure, and but just by looking into that, you can see if it is negative or it's positive. Depending on the test, I still have to check whether the sign always makes sense or not. But it tells you little more information.
To answer the question, what is the difference?
In this, the difference between the mean of the man and mean of the this, it will be around 1000 something, 1020, I think so. Yeah, 1020. So that's the difference. So you say that these two groups are different, and how much different they are? This is the amount, right? You can say the marks of two group in this two classes are different, and my test says it's significantly different. That's a one statement. But then another people might ask you how much different you are talking about. You say, oh, 1 marks. It's not that big. So that's what the question is, that significant doesn't mean meaningful. So is it 20 marks? Yes, it's a meaningful. Any other question? Good. So see you next. I think it's the 3rd of November, right? Next session.